Thokala Soloman Raju. He is an assistant professor in Department of Physics, ICFAI Foundation for Higher Education, Hyderabad, India. His area of interest is soliton in nonlinear waveguides, and also he works in the deep learning in nonlinear dynamical systems. So, Dr. Soloman Raju, the floor is yours.
Okay. Thank you very much, Riddhi, for introducing me. So, I will use online board, actually whiteboard I will use to deliver my talk. So, okay, so is my whiteboard visible to all of you?
Yes.
Yeah, okay. So the title of my talk today is Dark Solitons of BEC as qubits. So today the title of my talk is Dark Solitons of Bose-Einstein condensate as qubits in quantum computer. So usually we know that quantum effects strive to disappear for macroscopic objects. Typically, quantum effects become depreciated out into their classical averages, and therefore manipulation of quantum states relevant for quantum computation becomes unsustainable at the macroscopic level. However, BEC is one exception in the sense that the quantum effects are perceptible at the macroscopic level. We know that BEC is actually macroscopic quantum object, and the time scale on which this macroscopic quantum state can exist has been estimated from few microseconds to even 0.1 seconds. For such a long duration, this macroscopic quantum state can exist, and therefore we can use the dark solitons of this macroscopic quantum state as qubits in quantum computer for performing various logical operations in quantum computer. So that is my talk. So first of all, let me explain to you what are these solitons. Solitons are basically nonlinear waves, and they emerge as solutions of nonlinear dynamical systems when there is a delicate balance between
excuse me, Dr. Raju, are you writing something, because we don't see anything?
No, I'm not. Right now I'm not
okay,
writing anything. I'm talking only.
Okay, thank you.
So the solitons are the nonlinear waves, and they are the solutions of nonlinear dynamical systems, and they emerge as solutions of nonlinear dynamical system when there is a delicate balance between dispersion and nonlinearity. For example, in various systems, physical systems, dispersion, for example, dispersion, what it does is it flattens when the wave is propagating through any medium, whether it is linear or non-linear. When the wave is propagating through a medium, it spreads out as it propagates. After some time, what happens is that the very wave it spreads so much that the very wave is lost. On the other hand, we have nonlinearity. Nonlinearity, what it does is that when the wave is propagating through the medium, it shallows the wave. So there is a spreading of the wave, and there is a shallow effect of the wave. When these two effects balance with each other, then a nonlinear wave called soliton is formed, and this soliton, it propagates without change in its shape or velocity, amplitude as it propagates. So it has been experimentally observed. Solitons are seen in optical fibers. Solitons are seen in hydrodynamic situations. So for example, the tsunami waves, the long tsunami waves that are generated, they are the best examples of solitons in water, hydrodynamic solitons. For example, in 2004, the tsunami occurred in Sumatra Islands in Indian Ocean. So, and those tsunami waves, they traveled almost 1400, 1500 kilometers, and they went up till Port Elizabeth in South Africa. So they are none other than the solitons that have been generated because of massive earthquake that occurred in Sumatra Island in Indian Ocean. So there are solitons which are observed in optics, in the optical fiber case, and there are solitons observed in hydrodynamic case, and solitons are also observed in Bose-Einstein condensate also. So, for example, they have observed bright solitons and dark solitons in Bose-Einstein condensate. Okay, so let me explain to you just 1 minute. Yeah, let me explain to you the bright solitons and dark solitons. And before explaining bright soliton and dark soliton, let me tell you the equation that governs the dynamics of Bose-Einstein condensate. The mean field equation that governs the dynamics of Bose-Einstein condensate, particularly dilute Bose-Einstein dilute atomic vapors that are responsible for the formation of Bose-Einstein condensate, it can be described by a mean field equation called Gross-Pitavsky equation. So in the dilute atomic gas vapors case, it can be written as IH bar dou psi by dou T is equal to minus H bar square by 2m dou square psi by dou x square plus G mod psi square psi. So here H bar is having the usual definition. H bar is equal to H by 2 pi, where H is the Planck's constant. M is the mass of the condensate. And this term indicates the dispersion of the wave, or the diffraction of the wave. And G indicates the strength of the nonlinearity, and mod psi square psi indicates the cubic nonlinear interaction. Also, it indicates the atom-atom interaction modeled by this cubic nonlinearity. So, for example, when G is greater than 0, it is called the repulsive nonlinearity. It is called the repulsive nonlinearity. It is called the repulsive nonlinearity. And in this case, a dark soliton emerges as the solution of the Grasp-Patowski equation. So when G is greater than 0, it is called the repulsive nonlinearity. So the atom-atom interaction, there are many Bose-Einstein condensed atoms at almost T is equal to 0. So T is equal to 0 is a very ideal case, but at T is equal to few nanokelvins, most of the atoms are in the ground state. So these Bose-Einstein condensed atoms, they interact, and this atom-atom interaction is governed by this cubic nonlinearity, and G is the strength of the cubic nonlinearity. And for the case G greater than 0, it indicates repulsive nonlinearity. In this case, a dark soliton emerges as the solution of the Grasp-Patowski equation. Indeed, in Bose-Einstein condensed the sodium atoms, this dark soliton, in Bose-Einstein condensed the rubidium atoms, this dark soliton has been observed. Okay. On the other hand, we have for G less than 0, it is attractive nonlinearity. So G less than 0 is called attractive nonlinearity. And in this case, they have observed bright solitons as the solutions of solution of Grasp-Patowski equation. First, let me tell you what is a dark soliton. A dark soliton, is depicted as follows. So this is the amplitude. This is the amplitude. So this is the zeta variable. So what happens is that there is a dip or there is a notch in the intensity of the or the amplitude of the wave. Okay, so here it is uniform, here also it is uniform, but here there is a notch or there is a dip in the amplitude of the wave. So therefore it is called a dark soliton. On the other hand, we have bright soliton. Bright solitons are those solitons for which there is a peak in the amplitude. Okay, so this is the amplitude, this is zeta. So a bright soliton is a soliton for which there is a peak in the amplitude. Okay, so but in today's talk we are going to use dark solitons of Bose-Einstein condensate as qubits in the quantum computer. Okay, so let me also give you an idea of how to obtain the solutions of this dark soliton and bright soliton of Grasp-Pythagorean equation. So the first let me obtain the bright soliton. So the GPE reads as IH bar dou psi by dou t is equal to minus H bar square by 2m dou square psi by dou x square plus G mod psi square psi. Okay, so now going to a moving frame, zeta is equal to some alpha x minus vt. We can map this equation to an elliptic equation of the form f double prime plus af plus bf cube is equal to 0, where f is function of zeta. Okay, so from this GPE equation, by going to a moving frame, zeta is equal to alpha into x minus vt, we can map this GPE to this elliptic equation f double prime plus af plus bf cube is equal to 0. So here A indicates the detuning parameter and B indicates the nonlinearity parameter. So this B is directly related to the nonlinear strength G. Okay, so now it has been proved extensively that all the 12 Jacobian elliptic functions are solutions. It has been proved extensively that all the 12 Jacobian elliptic functions are solutions of this elliptic equation f double prime plus af plus bf cube is equal to 0. But in order to demonstrate the formation of the bright solitons and dark solitons in BEC, Bose-Einstein condensate, we consider only the solution. For example, f is equal to a secant hyperbolic A zeta. Okay, so if you substitute this solution into the elliptic equation f double prime plus af plus bf cube is equal to 0, this solution will be satisfied, and we will find that this bright soliton is indeed a solution of the Grasp-Pitavsky equation. Okay, so similarly, if we choose f is equal to some b tan hyperbolic d zeta, we can also prove that this is indeed a solution of the elliptic equation f double prime plus af plus bf cube is equal to 0. So this is the bright soliton. This is the dark soliton. Okay, so this is how we can demonstrate the formation of the bright soliton and the dark soliton in a BEC. Particularly, we can prove that the bright soliton f is equal to a secant hyperbolic a zeta as the bright soliton solution of the Grasp-Pitavsky equation, and also f is equal to b tan hyperbolic d zeta as the dark soliton solution of the Grasp-Pitavsky equation. Okay, so this is the background for my talk. The talk is entitled as dark solitons of Bose-Einstein condensate as quantum qubits. Okay, so I'm going to dwell more on these dark solitons because these dark solitons are found to be stable solutions. It has been proven rigorously. Also, we can prove by numerically simulating the Grasp-Pitavsky equation, and also experimentally, it has been proven that these dark solitons are more stable than the bright solitons, and therefore these dark solitons are used as quantum qubits in the quantum computer. Okay, so as I have already told you that quantum effects strive to disappear for macroscopic objects, but BEC is an exception in the sense that these dark solitons can be used as qubits in quantum computer. And moreover, the lifetime of the dark soliton as a macroscopic condensate is of the order of a few microseconds to 0.1 second. That is a huge amount of time for which these dark solitons can stay. So therefore, we can manipulate we can manipulate the quantum state, this macroscopic quantum state relevant for quantum computation, because it is sustained for longer time. Okay, so now let me get into the details of this dark solitons of BEC as quantum qubits. So let me describe to you the mean field equations and the dark soliton qubit. Mean field equations and the dark soliton qubit. We consider a quasi one-dimensional Bose-Einstein condensate immersed in a dilute gas of impurities. The BEC and the impurity particles are described by the wave functions. For example, so the one-dimensional dilute BEC is immersed in dilute impurities. So the BEC is described by the macroscopic condensate wave function psi1, and the dilute impurities, they are described by the macroscopic condensate wave function psi2. A quasi one-dimensional gas is produced when the transverse dimensions of the trap is larger than or of the order of the S wave scattering length, and at the same time much smaller than the longitudinal extension. At the mean field level, the BEC is governed by the Grasp-Patayevsky equation. So for this psi1, psi1 is governed by the GPE Grasp-Patayevsky equation. So let me write down this Grasp-Patayevsky equation. IH bar dou psi1 by dou T is equal to minus H bar square by 2m1 dou square psi1 by dou x square plus G11 mod psi1 square psi1 plus G12 mod psi2 square psi1. So this is the Grasp-Patayevsky equation that governs the dynamics of Bose-Einstein condensate. But this Bose-Einstein condensate is immersed in dilute impurities governed by the condensate wave function psi2. So there is a dynamical equation that governs the dynamics of impurities also. So for the impurities, the dynamical equation is IH bar dou psi2 by dou T is equal to minus H bar square by 2m2 dou square psi by dou x square plus G12 mod psi1 square and psi2. Please notice that the BEC condensate wave function enters into the dynamical equation for impurities as a nonlinearity. So G12 mod psi1 square psi2. So it is a coupled equation. These are two coupled equations actually. But here we assume that the impurities, impure particles, they do not interact as much as the BEC condensed atoms interact. Okay, so the interaction is very, very small. Okay, so in the Grasp-Patayevsky equation, we have the cubic nonlinearity, and the strength of the cubic nonlinearity G11 indicates one-dimensional coupling strength, and G12 and G21, they are equal. They indicate interspecies coupling constant, and H bar is having the usual definition H by 2 pi, where H is the Planck's constant, and masses M1 correspond to the mass of the Bose-Einstein condensed atoms, and M2 correspond to the mass of the impurities. Okay, so here in particular we consider the case we consider the case the cubic nonlinearity in the Bose-Einstein condensate is greater than 0. That means we consider the repulsive interaction case because the because the interaction is a repulsive interaction. Obviously we get dark solitons as solutions of the Grasp-Pitarsky equation. Okay, so we assume that the dark soliton is not disturbed by the presence of impurities. This we can achieve if we choose the impurity to be sufficiently dilute. That means if we choose mod psi2 square is much less than mod psi1 square, then we can achieve this object. So the impurities can therefore be regarded as free particles that feel the soliton as a potential. So in that case, the dynamical equation for the impurities can be written as, so in that case, the dynamical equation for the impurities can be rewritten as IH bar dou psi2 by dou t is equal to minus H bar square by 2m2 dou square psi2 by dou x square plus G12. So this psi1 is actually the solution of the Grasp-Pitarsky equation. So that goes in as a psi solution square psi2. So from our experience, we know that this dark soliton solution of the Grasp-Pitarsky equation can be written as the dark soliton of GPE can be written as psi sol is equal to square root of n0 tan hyperbolic x by zeta. Here n0 indicates the background density and zeta is the healing length. Zeta is the healing length and it is given by h bar by square root of mn0 g11. In literature, many people have also found gray solitons for the GPE equation to compare with this dark soliton with that of the gray solitons. So let me write down the gray soliton solutions also. The gray soliton so the gray soliton is actually is equal to square root of n0. N0 is the background density, I theta plus 1 by gamma tan hyperbolic x by zeta gamma, where theta is equal to V by CS, gamma is equal to 1 minus theta square to the power of minus half, and this CS is equal to square root of Gn0 by m. It is nothing but the BEC sound wave. So our dark soliton is comparable to the gray soliton that appear in literature in many research papers. So this gray soliton and the dark soliton, they are related actually. So, but here we are specifically considering the dark solitons of the Bose-Einstein condensate as qubits of the quantum computer. So this is only for comparison I am writing. Okay. So now we consider the time independent variation of, now we consider the time independent version of the dynamical equation for the impurity as minus h bar square by 2m dou square psi 2 by dou x square plus G21 n0. So our solution, the dark soliton solution of the Grasp-Patowski equation, psi solution is actually square root of n0 tan hyperbolic x by zeta. That's what we have taken. So now we will substitute this into the dynamical equation for the impurity. So that becomes tan hyperbolic square x by zeta psi 2 is equal to E psi 2. So this looks like the usual linear Schrodinger equation. So to make it more transparent, I will bring it to this. I will simplify this. Dou square psi 2 by dou x square minus G21 n0 secant hyperbolic square x by zeta psi 2 is equal to E prime psi 2, where E prime is equal to E minus G21 n0. So if we can see that in this equation, minus h bar square by 2m dou square psi 2 by dou x square minus G21 n0 secant hyperbolic square x by zeta psi 2 is equal to E prime psi 2. This is like quantum eigenvalue equation. H psi is equal to E psi, right? So this part indicates the potential, right? So this potential is actually very interesting potential. It is secant hyperbolic square x by zeta. Okay. So here the dark soliton acts as a potential for the particles of the reservoir. Analytical solutions to this equation can be obtained by casting the potential term as V of x is equal to minus h bar square by 2m zeta square nu into nu plus 1 secant hyperbolic square x by zeta, where this nu is minus 1 plus square root of 1 plus 4 G12 by G11 by 2. Okay, so this potential looks like a reflectionless potential where the wave undergoes fully transmitted. Okay, so by casting this potential in this form, we can obtain the solutions of many analytical solutions of this equation can be obtained. Okay, so and the energy spectrum associated with this potential can be written as the energy spectrum associated with this potential can be written as En prime is equal to minus h bar square by 2m zeta square nu minus n whole square, where n is an integer. So the number of bound states is given by n bound is equal to 1 plus nu plus square root of nu into nu plus 1. Thus, a two-level quantum system qubit can be perfectly isolated when the value of nu ranges as nu 1 by 3 and 4 by 5. At the critical point, nu is equal to 1 by 2, the two energy levels will merge, and the qubit is ill-defined. The qubit is ill-defined. Okay, so thus we have shown that the dark solitons can act as a two-level quantum system or the qubit of the quantum computer. Okay, so what I have shown in this talk is that the dark solitons indeed act as the dark solitons of the Bose-Einstein condensate really act as the qubits of quantum computer. Okay, so there I end my talk. If you have any questions, please ask me some questions.
Any questions?
In general, on solitons also, you can ask any question.
I have questions. Can I ask?
Yeah.
Thank you. So, thank you for your talk. In your talk, you consider 1D soliton, and they are stable over time.
Yeah.
So, any reason why 2D solitons are not considered? Because first of all, they are not stable. So I just want to know why those are not considered. Any reason behind that?
Yeah. Two-dimensional solitons, they are in general, two-dimensional solitons are not stable actually.
Yeah.
So that is the reason the condensate that is formed, the macroscopic condensate that consists of these two-dimensional solitons, I think its lifetime will be, first of all, they are not stable. So we cannot use them as quantum states in a quantum computer.
Yes, it is clear, but okay. So could you suggest references where 1D soliton is considered as qubit? So I think this 0 and 1, like in qubit, we have 0 and 1. In soliton, you are proposing use 0 as dark soliton, use 1 as bright soliton. So this is a mixture of 0 and 1, right?
Exactly.
So could you suggest references where dark and bright solitons are used as qubits?
Yeah, it is a proposal, and I can give you right now. I don't have many references, but I can give you afterwards. Actually, I will. There are some physical review yes and physical review letter papers also, where they have mentioned the usage of dark solitons as qubits in quantum computer. I can give you some references actually.
Okay, because it is interesting. It's like very similar to Schrodinger cat states when you have two macroscopically distinguished states, and in between them there is a interference. So in your case, I think it should also be some interference should be there between two states like dark and bright soliton. So did you consider also this interference pattern, or did you see this interference pattern between two solitons?
No, generally solitons, when they interact, there will be no interference actually.
Okay.
Because there is an elastic collision between them, and when two solitons interact, they interact in such a way that they have not seen with each other.
Yes, but I mean, the wave function should be there should be overlap when they like passes each other, should be overlap wave function. So
Yeah, only there will be a phase change. That's all. So
okay,
that's all.
okay, because in that way they can exchange the information inside each soliton.
Exactly.
Okay, thank you.
Thank you very much. Thank you very much.
Any other questions from the audience? So I have a question.
Yeah.
I mean, can you, you are saying that in the beginning you said that you can create solitonic waves in different kind of medium. So can you generate solitons from acoustic wave?
Definitely, definitely. Acoustic solitons are also there.
And can you create them inside BEC?
Yeah, why not? They have seen
Okay.
experimentally in lithium, and I can give you, see, there are science papers actually. They are science papers where they have seen these bright solitons and dark solitons. Both are science papers actually.
Okay. Thank you.
Okay, thank you very much. Thank you very much.
If there is no other questions, so let us thank the speaker.
Okay, thank you. Can I come out and log out?
Dr. Solomon, can you also share your email address so that I can ask you question regarding the references?
Yeah, please. Please note down my email ID. PS Raju at ICFAI.org. PS Raju @ifeindia.org.
Thank you.
Okay, thank you very much.